All right, welcome back. We're going to do a couple more examples of using substitution to find indefinite integrals. And the first example that we are going to look at today is example 6, which is rewriting trig equations. We know a lot of relationships and we know a few antiderivatives. So let's see if we can put that together. Let's start with the cotangent of 7x dx. Well, we know that cotangent is cosine over sine. So we need a substitution. So let's look at a couple possibilities. First of all, u is equal to cosine of 7x. The differential du is 7 times the negative sine of 7x dx. Notice that we do not, in fact, have a sine of 7x dx in our equation because the sine is in the denominator of the equation. So that's not going to work. Let's put a little red X through it to show that it is not going to work. And our other possibility is that u is equal to sine of 7x, giving us the differential du of 7 times the cosine of 7x dx. And what I now see is that, in fact, I have a cosine of 7x dx right there in my equation, which means that my equation now becomes, well, I need to put a 7 in front of it. Which means I need a 1/7 to balance that out. This whole thing on top is my differential du. This whole thing on the bottom, once I stick the 7 into the sine of 7x, is my u, which means that I now have the 1/7 the integral of 1 over u du. And of course, that is 1/7 natural log of u plus a constant. Going back, plugging in my function of x, I've got 1/7 natural log of sine 7x plus a constant. And there it is. I'm done. That's the antiderivative of cotangent of 7x. If you are skeptical, you could spend a little bit of time actually taking the derivative of 1/7 natural log of absolute value of sine of 7x plus a constant and see if you get cotangent of 7x. And if you totally believe me that everything I did was true, you could do exercise 29 out of the book and then come back for the next example, which is example 7. And let's look first at the integral of dx over cosine squared of 2x. And notice dx over versus 1 over times dx, of course, the same thing. I probably didn't need to say that, but I will say it anyway. Well, we know that 1 over cosine is secant, so this is the integral of secant squared of 2x dx. We're going to let u equal 2x at this point. Now, to be fair, this is probably one you could just do. You know that the antiderivative of secant squared is tangent, and there's a 2x, which means you're just going to have a chain rule, which means you're probably going to have like a half out front. But we're going to go ahead and do this doing substitution so I can prove to you that, in fact, this works even for these simple ones. The differential du is 2dx. I need to plug a 2 into my equation. Which means I need a 1/2 out front. This is now 1/2 the integral of secant squared u du. Of course, as we said, the integral of, or the antiderivative of secant squared is tangent. So we have tangent of u plus a constant. But u is 2x, so we now write this as 1/2 tangent of 2x plus a constant. All right, that was a pretty straightforward one. Let's do a slightly less straightforward one, the integral of cotangent squared of 3x dx. And notice that got to be a little bit careful here because we don't want to go too big on our u by saying, oh, let's make it cotangent squared of 3x, because then the derivative is, well, don't know. We could look it up. It's some weird complicated thing. And guess what's not in this integral? The weird complicated thing. So we don't want to do that. So this time, because we don't have an antiderivative of cotangent squared, so making u equal to 3x doesn't actually help us. But what we do know is that there is a trig identity that says that cotangent squared is equal to cosecant squared minus 1. Hey, we know this one. We'll let u equal 3x. du equals 3 dx. We'll shove a 3 in here and a 1/3 out here. So this becomes 1/3 the integral of cosecant squared of 3x minus 1 times 3 dx. And I recommend that you write this out every time for now. If you try to skip steps, you're going to forget something. You're going to mess it up. Just write it out. It's tedious. Yes. Do it till you get good at it. I'll be honest with you. I've never really gotten to the point where I can just bang through these without writing out all the steps. That's just how my mind works. All right, let's continue. 1/3 the integral of cosecant squared u minus 1 du. We know that the antiderivative of cosecant squared is negative cotangent. We know that the antiderivative of 1 is, now be careful, this is in terms of u plus a constant. And now finally, we're going to go back and we're going to plug in negative cotangent of 3x minus 3x plus a constant. And we now have our integral. I am going really slowly here because, oh, never mind. Nope, we're good. There you go. You can get rid of the parentheses, distribute the 1/3 if you want, but I'm not gonna. All right, one more, and then this will be a slightly excessively long video, but will have 3 examples under our belts. The integral of cosine cubed x dx. Now, again, there's nothing inside the cosine that we would want to make into u, because putting a u in there makes no difference. If we make cosine cubed equal to u, well, then we've got a little bit of a problem. But what we could do is we could split this up into cosine squared times cosine x dx. And hey, I have a relationship between cosine squared, which tells me it has to do with sine squared, and the derivative of sine is cosine, so maybe I'm onto something here. I rewrite this as 1 minus sine squared times cosine x dx. I'm going to let u equal sine of x. That means that the differential du is cosine x dx. Hey, look, there it is. There's du, which means I'm asking for the integral of 1 minus u squared du. Hey, this is a polynomial. It's super easy. It's u minus 1/3 u cubed plus a constant. And then plugging the signs back in, I get that it is equal to sine x minus 1/3 sine cubed x plus a constant. And boom, the antiderivative of, or the integral, of cosine cubed x is sine x minus 1/3 sine cubed x plus a constant. All right, we're going to call it good here. We will come back next time with definite integrals where we've got boundaries of our integral. In the meantime, my students, go ahead and do exercise 47 out of the book. I will see you next time. Thanks for watching.